Okay, hello everyone. Good morning. So today we are going to have some exercise on chapter 3. Uh, Hopefully I can do 3 questions for today's class. Okay, let's start with the first one. So I think this is, I have put the notes on these questions, I think, last week. And after today's class, I will upload the exercise notes so that you can discuss and work on other questions as well, because I think we still have some questions that still need to be solved. Okay, we start from this question of these 3 members. They are attached together, supported by 2 rigid walls, and they are going to undergo the axial deformation due to the load P as shown in the figure. And then member AB is solid brass. It has the diameter 25 millimeter. It has their own modulus 100 GPa. And BC is steel pipe. It has outer diameter 25 millimeter and inner diameter, okay, which is 20 millimeter, and modulus is 200 GPa. And then member BD, the small one, the inside of BC, so it's a pipe. BD is aluminum alloy. It has diameter 12.5, modulus 70 GPa. L1 is equal L2, which is 0.5 meter, and L3 is 1.25 meter. Calculate the displacement UD of the point D where the load is applied, okay, 9 kilonewton applied. And then calculate the axial stress on the BC, okay, the element 2. So we have 3 elements. We have 3 elements, that is, so if you see the how the question is formed, I hope you get the what happened within this. Okay. So we have a wall. This is also a wall, but they are having a hole inside. So within this hole, the element 3, the BC and CD, so they have a different element, but the problem here is we applied some forces on this D. It can generate reaction force throughout the system and then make some displacement on this D, but here they are attached to the wall. Okay? So they are only getting exert only on this inside of the pipe. Okay? So if we try to check out the diagram, or if we want to draw the schematics, we can try to firstly we can look on, perhaps the easiest one to be separated is this part, right? We can see that only we have only load P and reaction force in element 3, right? So if we take that as our diagram, so our free body diagram, so suppose that this is the D, okay. So this is element 3. We have the load P and we have reaction force. Let's say we have F3. Okay. Now from this FPD, we know that the F3 will equal to P will equal to 9 kilonewton. Okay. I think easy to follow. And the second diagram that I think we need for our equilibrium is a joint where all the three elements can have some intersections. I believe that will be the joint B. Okay, because if you see joint B, you get the element 1, you get element 2, and you get the inside one, the element 3. Okay? So you get 3 elements in one joint. So let's say this is the B, okay? And let's say this is the B here. Let me make it. Okay. And then we have the inside. Let me copy. So the inside one is the element 3. So let me draw element 3, just a little bit like that. This to show that this is element 3, this is element 1, this is element 2, right? So in element 3 we have F3, we have F1, and we have F2 over here, supposedly. Okay. Because it's surroundings the element 3, so I will just imagine that the F2 they have this much of force, but I will just write that all the forces will be as a resultant of F2. And by equilibrium, taking the sigma of Fx equals 0, we can have F1 minus F2 minus F3 is equal 0. Okay, so we have all this to equilibrium, and I believe that is the first starter. Okay. The second part is it will be having some displacement, right? It has some displacement, so we can write down so every time you are dealing with problem in axial deformation, we can start by just start by writing the formula F L A E. Okay, we can simplify. We can simplify this L over AE, or if you want to make it into the F equal E, and then this will be AE over L. This is also can be done, and we can simplify the AE over L. Usually this is F, this is K. Okay. But this is just the name. Okay, if you forget which one is F, which one is K, it doesn't matter as long as you can simplify it either through the displacement or through the force. Right? They are both the same. Okay. We are going to use it differently. It depends on the case. Okay. So in our case here, since we have the forces mentioned in the diagram, then I think we can make it, and we can count or compute the K, because we all have all the numbers, right? We have the E, we have the area, we have the length. So I think we can find all these numbers and we can write as if it is. So we can write the F1 is K1 E1, F2 is K2 E2, and F3 is K3 E3. Okay. And then we can first find the K1 is A1 E1 over L1. So for the first one, we have the diameter is 25 millimeter. So pi over 4, this is 25 millimeter squared. And then E is 100 gigapascal. Or you can write as this is 10 with power of 3 Newton over millimeter squared, and over L1 is 0.5. .5 meter, but I will write with the 1000 to get into millimeter. You can compute this, and we get that this is around 98.174 kilonewton over millimeter. The same thing with K2, but K2 is hollow, so we need to compute the area by subtracting the diameter. So this will be A2 E2 L2. This will be 25 and 20 squared, right? The inner diameter is 20. And then E is 200. And we need to divide by L, which is L2 is equal to L1. Okay, you can calculate, and this will be around 7.685 kilonewton per millimeter. Do the same thing with the K3. I think to shorten our time, I will write, just skipping all the numbers, I will write directly what will be. This is kilonewton per millimeter. And then we can focus on the geometry. So in geometry, we have that is, I think we could see that when we exert the load, the joint B will have extended to the right side. So element 1 or member 1 will have some increasing in length, right? So we can agree that so let me write, this is for the geometry of deformation. So our E1 is exactly the displacement of UB. So since E1 is going to be decreased, E1 is going to be increased, and then the element 2, we can think that this is going to be the negative part of UB, okay, from our picture here. So because it's going to be increasing over there, so element 2 will be going to be decreased. So UB will be negative E2, or E2 is negative UB. And then for element 3, we have another displacement of UD. So we have some extension, but we have the length is from here, right? So we have extension here, but this one, the same with the element 2, it will be going to be, you can think this as a minus in terms of UB. Okay. So if we consider the first element is increasing, then the second part and the third part, because they are in line in one segment, they are going to be negative displacement of UB. Okay. So what will happen here is we are going to have, this will be UD minus UB, or minus UB plus UD. Okay. And then from all of this geometrical deformation, we could combine this E with our F1 formulations, and F1 can be take equilibrium with the first equations here. So then we can start taking the all of the elongations. So first we can write that the F1 is K1 E1. K1 we already compute. So F1 is K1, or perhaps E can be represented as UB. Okay. And maybe let me rewrite this as F1 minus F2 equal F3, or F1 minus F2 equal 9. We can directly use that, or let me write directly here, so that I don't want to write double. So F1 is K1 E1 minus K2 E2, and we can write this as K1 UB minus K2 E2 is negative UB. So this will be UB K1 plus K2, 9 kilonewton, and we can get UB from this expression. K1 plus K2 is 98.174 plus 70 points. This is kilonewton per millimeter. So we get to divide this, and we get that the UB will be 0.05 around millimeter. Okay. So we get UB, and what else do we need? We need to compute the UD. Okay. So UD is getting from, I think I will make it to the left. So E3 is F3 over K3, or 9 kilonewton over K3. So this 9 kilonewton over K3 is 6.872 kilonewton per millimeter, is equal UD minus UB. So UD 6.72 kilonewton per millimeter plus the 0.053 millimeter. So we get UD is around 1.36 millimeter. Okay. So this is the first part that we are being asked, the displacement of UD. The second one is compute the axial stress, okay, the BC section. Okay, BC section. So axial stress. So for part B, so axial stress on element 2, or in BC section, is F2 divided by area 2, right? And F2 we get from this part, K2 E2, and we have everything compute, right? So K2 E2 divided by E2, and E2 is actually, E2 is negative UB. UB is this, so we can exchange everything. So K2, this is negative UB divided by A2. And K2 we have done. K2 is 70.685. And the UB is 0.53. And then the A area for 2 is pi over 4. This will be 25 millimeter squared minus 20 millimeter squared. And this will be around 21.2 megapascal. Maybe number will be a little bit different if you compute, but I think still similar, so I think still okay. So we get already all the questions on this problem. Okay. So basically the key component of our problems is we need to have the axial deformation formulations. Okay? Either using K or using F. We can compute all the variables in, or all the components in the axial deformations. So we are left with the force and elongations. So that's actually the component, how we can differentiate between the basic force method and displacement method. I don't want you to confuse on the terms or the method, or which method should I use, but rather what you need to do is you need to figure out the equations. Okay? You need to figure out the system of equations. For example, you need to figure out, oh, we have this, and we have the E that we can get from our formulations in terms of the geometric of the formation. So we can have this, and then we can substitute to our F into our equilibrium, and then we can get all the displacement, and after the displacement we can also compute the stress that we need. Okay. So that's the formulations. So either that is the first possible questions, a typical questions. The second typical questions is we can have the equation that we solve is E. Okay, maybe we have some compatibility equations. Like for example, if we add all the elongation, it will be 0. That means the formulation from E from here we can substitute so that, and the relation from F we can get from the equilibrium. Okay. So this is, I think, a typical case. So as long as you can define the equilibrium, you can draw the diagram correctly, get the equilibrium, and then get the system of equation of the elongations, and then substitute, either substitute elongation to the force or the force to the elongations. Okay, you can do both ways. Okay, and then solve, and you get the, either you can get the displacement or you can get the force. Okay, so I think that's the key. As long as you can do that, it should be okay. Okay, let me continue. Okay, this is another one, but I think I will focus on the next part. This part, the key is, if you remember when we have this member here, it will be bent. It will be bent, and assumption for the bending on this topic will be the rotation is very small. Okay, so this, because it's rigid, so the angle here will be very small rotation. Very small rotations, which means that we can, if we have this, and suppose that this is the rotations like that, So let's suppose that this is the theta, and this will be okay. Suppose this is going to be the length. Let's say up until here, this is A. So this is another A, maybe up until there. So you have some displacement. We have some displacement for two parts. So the first part is here. So displacement, which is bent, and then the other part is getting bent on the other side. So because the angle is very small, what you can do about it is actually you can use the tangent. Tangent means this and this, right? So we could imagine the tangent. We can use the tangent, and the tangent for both triangles. Okay, but remember, when the angle very small, the tangent value is similar to that angle. So we can have approximations, okay? Because theta very small, then we can write this as our approximation. Okay, this is just additional information to help you solving this part. Okay? And then the rest, it will be depend on the force deformation equations. Similar to what we have before, we have F1, K1, E1, F2, K2, E2 for element 1 and element 2. And then solving the equation, and we get the theta, we get the rotations, and then we can have the axial stresses for both of the element. Okay. If we have time, we can go back here and solve, but I think due to the time, I will continue to this part. Okay, this one is more likely to be concept fundamentals questions. So you have the 3 elements. You have the condition is attached to the walls. So we can have the compatibility equations, which is because of the walls, then we can write then the geometry of the formation. It will be E1 plus E2 plus E3 is equal 0. Okay. Okay, but maybe before that, I think I can write the geometry on the left side. We can write the free body diagram. We can either taking the 1 and 2, join B or join C. Okay, so we can have 2 joint because they are going to include everything, both of the joint. So we can start by taking the joint B. Okay, so this is, let's say this is B. So let's say this is, we have P on element 2, but we have reactions on 1 here. Let's say this is 1, F1, and this is F2. So this is element 1, element 2, and this is B. Okay. And the other part is on C. And we have another P and this will be F2, and we have F3. This is 2, 3, C. Okay. Okay, I think equilibrium is okay. So F1 is equal to F2 plus P. Here is F3 is equal to F2 plus P. So F2 plus P is equal F1. F2 plus P also equal F3. So F1 and F3 should be equal. And then we can write down the elongations formula. E is F, L, A, E. Since we have F and we have the geometric deformation is in terms of E, so I think it's better to let the LAE to be computed first. Okay, if you have the numbers, this is a principal question, it doesn't have numbers. So I will change L over AE with the small f to make it easy to follow. But in the real calculation, that will be a number, and you can compute that first, okay, to make the equations easier. So we can compute, and suppose that we have this L over AE as small f, then we can have E1 is F1 small f1, the same thing with E2 and also E3. Okay, now the next is our A and E will be based on the information given. The A1 is equal to A3 is A, A2 is 2A, L1 is 2L, L2 and L3 will be L. So we can all change with that information. So we can have F1 is, let me write L1, A1, E1. L1 is L, or 2L, sorry. A and all the same E. Okay, we have everything correct. Now substitute. So F1 is F2 plus P. So we can write here the component. I think I will write the component on downside here, and I will substitute the F1. So F1 we can write the or I think we can write this. So E1 plus E2 plus E3 equals 0. So F1 plus F2 plus F3 okay, equals 0. So F1 I will change to F2 plus P, and F1 is 2LAE plus F2. So I think we can compute F2 for this first one. This will be L over 2AE plus F2 plus P. F3 is LAE. And we can solve the F2 from here. I think think you can cancel this, all this AE, L. I believe we can cancel that. So I will write the final results, okay, without this will be 3L AE, or let me write the final results. Negative 6/7p, okay, after we solve this. The F1 is equal F3 is equal negative 6/7p plus p. So this will be 1/7p. Okay, so we have F1, F2, F3 already. Then we can have the sigma. So sigma 1 is 1/7p over A. A1 is A, so this will be p/7a. Sigma 2 is F2 over A2. A2 is 2a, so this will be over this will be negative 3/7p/a. And the same thing with the third stress, F3/A3. It's the same with stress 1. Okay, so we get the stress. This is the first job done. And then I forgot the second question. Determine the expression for horizontal displacement UB and UC. So UB, we can see from here that UB is equal to E1, and UC, since it is increasing on the element 2, element 3 is decreasing, but we can agree that in elongation 3 it should be negative UC, right? So our UC is negative E3. So E1 is F1 force 1, okay? This will be 2L or 2PL over 7EA. This will be for UB. And UC is from E3 is this will be PL over 7EA equal negative UC. So UC is negative PL over 7EA. Okay, so basically, after you get all the solving the equation, get all the force, get all the displacement, you can figure out each stresses and then figure out the specific displacement on the joint. So this is UB, UC. Okay. Okay, any questions so far from this previous one? And this type of questions, it can be have more combinations. Like for example, it's not only like 1, 2, 3 elements. We could be like maybe we have more joint, like maybe 5 elements or 6 elements, but the principles still stay the same as long as you can make the every joint, you can make out the diagram. You can have the relations between all the forces, and you can also relate to the axial deformations and get this formulations, and then having this compatible equations. You can basically solve simultaneously, and I hope you can do that. And I believe taking like for example, you have the system of equations. Perhaps sometimes it will be a linear equation. I hope you can solve the linear equations either by taking the substitution method or eliminations, or even if you want to know, or if you want to utilize the some of the matrix elements, you can turn this into matrix if you want and use the Cramer's rule or the Gauss elimination method as well. Sometimes it works for, imagine that if you have like a lot of joints, you have a lot of variables here, right? If you are solving one by one, it will be really tedious. So some of the methods could be works. And I think some of your calculators could be also solving this linear system. So it should be also possible to use that. Check your calculator if you can. I think for linear equations should be, for most scientific calculators should be available. Okay, like for example, here we have 5 elements here with the same length for each element. So at least we have 5. So we have 5 elongations. Okay? So we have E1, E2, E3, E4, E5, and we can add all of them equals 0. So the principle is the same. So the difficulty is just it will take more time because we have many joints. But it will be very similar to the previous one. I think this one is similar to the previous 2 questions. Okay? You can try to exercise with this from the method done in the previous example, and then the same method or the same assumptions. The angle will be very small. Okay? So we can use this in terms of tangent, which is equal to the angle itself, okay, because it's very small. Okay, another type of questions, I think, yeah, this is the same as the previous one, but this one is having the temperature. Okay? So temperature will add it into your elongation. So your elongation is not only the FLAE, but also the temperature. Okay? With the alpha, usually we have the alpha. Yeah, we have the alpha and the delta T, and that will be just, so your elongation will be just plus the temperature, okay? Force and then plus the temperature. Okay? The difference is just that. I think that's it. I believe if you are familiar with the solving the previous example that I showed you, whatever I put the combination in the questions, as long as you stick with the principles, it should be okay, because I think the difficulty will be the process. But if you stay with the principles and you start off with the correct assumption, correct method, although maybe your computation might be wrong in the middle, or maybe you miss something, you still get I think a majority, the percentage will be higher, okay? As long as you stay with the principles. So I think I will end the class up until that part. So hopefully next week you can do your best for our